Our next speaker is Rebecca Goodman, and Rebecca is a master's student in food science in the Ozturk lab at UW-Madison. She earned her bachelor's degree in food science, focusing on product development and organic chemistry. Please help me welcome Rebecca to the stage.
So thank you for the introduction. As stated, I'm Rebecca. I'm a master's student in the Ozturk lab. And today I have the opportunity to talk about my research, which is the effects of thermal treatment on whey protein concentrate. So if you were here last year, I talked about whey protein phospholipid concentrate. This is not quite the same topic. So I swear it's different. Whey protein concentrate is a pretty major dairy ingredient produced as a result of cheese manufacture. Its amount kind of fluctuates from month to month. Currently this year, we've been seeing about 35 to 40 million pounds per month produced. And it's made in these large amounts because on top of it being a very useful co-product from cheese production, it has all sorts of applications in health and protein foods and like emulsifiers and just general nutrition. However, what I really want to focus on today is its role as a precursor for whey protein isolate and whey protein phospholipid concentrate. So your whey protein concentrate, sometimes you, like I said, you sell it off as is and use it as an ingredient, or sometimes it's further fractionated into a purified whey protein stream, and then this retentate stream full of residual proteins, caseins, and milk fat globule membrane components. So, and just as a quick review, milk fat globule membrane is that complex structure that surrounds the triglyceride core of a milk fat globule. Several people in my lab and collaborating labs are researching potential uses for MFGM. And it's got a variety of like phospholipids, bioactive proteins, so forth. So why are we studying this? We're studying this because whey protein concentrate is a fairly involved process. You start out with your production of cheese. You take your whey, skim the cream off of it to get skim whey. Then that goes through ultrafiltration to make a whey permeate stream, which another lab member studies, and whey protein concentrate. And this whey protein concentrate can be, again, sold off as an ingredient, or it might be further processed into that purified whey protein isolate and that co-product WPPC. Along the way, there's a lot of heat steps, such as in the US, we're almost always starting with pasteurized milk for now. We also have at the skim whey state, you often are going to pasteurize here because you want to stop all the enzymatic activity and or microbial activity from the cheese production before continuing down into the filtration. Whey protein concentrate, if it's sold as is, might be pasteurized or spray dried, or it might be pasteurized before being further processed into your whey protein isolate and or your WPPC. And this combined with all of this physical processing that's occurring from like the shear of the pumps and the HTST and all the filtration and that time under heat and shear can result in some production pitfalls. And what I mean by that is on top of what you would generally suspect, which is like the enzymatic proteins and MFGM losing enzyme activity, or your lipids and proteins having increased oxidation, a big pitfall is the aggregation of whey proteins, specifically beta-lactoglobulin. This aggregation can cause a decrease in whey protein isolate yield if you decide to separate out your whey protein concentrate from your MFGM components. This also means that if you are a company that's interested in selling MFGM components, they are a less pure source because of all this residual whey proteins. So what I'm trying to do here is understand these thermally induced processing modifications that WPC protein and lipids undergo in order to create more efficient processing strategies for higher yield whey protein isolate ingredients and ideally higher quality MFGM components. And so how we did this, in my lab, we have been doing some in-house WPC / WPI processing. It's on a pilot scale, so we start with whey either from Babcock cheddar production or for one special case, raw cheddar production with the help of the Center of Dairy Research. And we skim off that and start with about 950 liters of skim whey. This then gets ultrafiltered for a 5x concentration into liquid whey protein concentrate. And then we further concentrated that with a 10x concentration using microfiltration into liquid WPPC and liquid whey protein isolate. This is the general framework of how our trials went, how the trials differ from each other. In addition to that initial cheddar whey being from raw cheddar versus regular cheddar is pasteurization and what kind was applied and how much was it applied. We used two types. One was batch pasteurization, where we used 63C for 30 minutes. The other was your kind of classic HTST pasteurization, 72C for 15 seconds. And so we ended up with these two processing flow diagrams. To highlight the one on the left, this is what I'm going to refer to as batch processing. And we start here with our raw milk cheddar. We batch pasteurized the skim whey, and then we have this batch whey protein concentrate that is then further fractionated into whey protein isolate and WPPC. On the other side, we have commercial processing, in which we start with cheese whey that was produced from HTST pasteurized milk. The skim whey receives another HTST pasteurization. We get our whey protein concentrate, or 2x HTST WPC, and then that is pasteurized again to get a more excessively heated WPC. So again, here's the two in review, and here's our three samples we're looking at. Batch, 2H WPC, 3H WPC in ascending order of heat applied. And then we did a variety of tests to look at how this WPC might have, the effects of this WPC might have on downstream products. So the first thing I want to do is just confirm using SDS page, okay, are our samples actually comparable to each other? So I have a non-reducing and a reducing gel. And what we can see here is that, yes, our protein profile is very similar, where we have our larger MFGM proteins. Underneath that are smaller caseins, and then underneath that are smallest and most predominant proteins of beta-lactoglobulin and alpha-lactalbumin. Additionally, in our non-reducing gel, we do see some level of aggregation up in the loading wells, indicating some level of disulfide bonds. But overall, yes, these are very comparable products to compare. Starting with some microstructure data. This was confocal laser scanning microscopy. Our proteins are dyed green, our fats are dyed red, and right away we can look at this and see that our moderately heated 2-HTST WPC has visibly smaller fat globules and aggregates compared to the WPC that received that additional HTST treatment. We also see that it has smaller aggregates than the batch WPC. So although batch WPC was more minimally heated, it still has larger aggregates. And this trend holds true when we look at the particle size measured with dynamic light scattering. So this is measuring things on a smaller scale. And again, we see particle size increase significantly with an additional HTST treatment, and we see our minimally heated batch pasteurized WPC also is significantly higher than our 2H WPC. Finally, if we look at one more microstructure, we can look at the zeta potential. So this is the net charge of all the particles in the solution, and we see here that batch WPC has the most negative zeta potential, meaning it should be arguably it should be more stable and less likely to aggregate further down the line. So yes, batch WPC has larger aggregates, but also they're possibly more stable. Moving on to some protein analyses. This is carbonyl content data. It's very useful for our lab to measure protein oxidation this way because it is heat-induced, it's functionally reversible, and right away we see this interesting trend where our batch pasteurization causes significantly more carbonyl content than our moderately heated 2-HTST WPC. We also see that third HTST treatment significantly increases the protein carbonyl formation. So again, this kind of reflects that the particle size data, where we're seeing some effects that we don't necessarily want to see in the particle size increase and in the protein oxidation increasing with additional HTST and with batch pasteurization. Another protein test that I ran was measuring enzyme activity of one of the MFGM proteins. In this case, we selected xanthine oxidase because it can be detected fairly easily with a fluorescent method. And what I found here was, if you look at this, our batch pasteurized WPC, which you could argue is our minimally processed WPC, actually resulted in a greater loss of xanthine oxidase activity compared to those that received HTST treatment. Now, if you look at similar data for milk that's been batch versus HTST pasteurized, you'll see a similar trend. This trend also exists with our WPPC data, indicating that, at least for xanthine oxidase, this enzyme activity is lost because of time under temperature, not just the intensity of the temperature itself. And then the final protein test I want to talk about is quantifying beta-lactoglobulin using HPLC. Again, this is very important because we're looking at, we're trying to see how much of that free beta-lactoglobulin exists in our WPC versus stuff that's been bound up with in aggregates with MFGM or other whey proteins, because if they are all aggregated, we're going to have presumably lower yield of whey protein isolate proteins. And what we have here is significantly more free beta-lactoglobulin in, again, that moderately heated 2x HTST WPC. And if we think back again to that particle size data, we see that it reflects what we would expect, meaning that we have higher free beta-lactoglobulin in a sample that also has smaller particle size, and our samples that have less free beta-lactoglobulin have larger particle size, again indicating increased particle size, decreased free beta-lactoglobulin, and presumably a decrease of whey proteins in whey protein isolate. For my final tests, I did was a little bit of lipid oxidation. I measured it in two ways. One was our primary lipid oxidation product of lipid peroxides in the form of peroxide value. And then a secondary product I wanted to measure was malonodialdehyde in the form of T-bars. For both of these methods, I extracted all of the lipids out to try to reduce any interference from the proteins or the sugars that are residual in WPC. And what I found here is that although we do see a slight trending increase of lipid oxidation for lipid peroxides, they're actually not significantly affected by the difference in heat or the difference of heat intensity. However, when we look at our secondary products, we see a pretty marked decrease of T-bars in that minimally heated batch sample compared to the 2x HTST and the 3x HTST whey protein concentrates. So what does this all mean? The big takeaway that there's three big takeaways I want to point out. One is that, yes, these repeated thermal treatments, as we saw whenever we compared 2H versus 3H WPC, definitely alters aggregation behavior, oxidative stability, microstructure, and so forth, which means it would also presumably affect our whey protein isolate yields. However, minimal thermal processing does not necessarily result in your optimal functional properties. Again, we saw that increase in particle size with batch pasteurization, and we also saw that decrease in enzymatic activity with that batch pasteurization. So overall, my takeaway right now is just that moderate HTST treatment can promote some improved whey protein isolate processing, and also may retain the xanthine oxidase activity and so forth a bit better than trying to go very minimally heated. When it comes to future research, a big one that I want to look at is whey protein isolate fractions. So I've looked at WPC, I've looked at one of its products, WPPC. Whey protein isolate is the last piece of this little puzzle, especially when it comes to beta-lactoglobulin content. And then the other thing I'd like to do is just characterize that secondary structure of whey protein concentrate a bit more. And I have a method using FTIR for this, but I just have not quite gotten around to doing that. And then I just want to acknowledge the lab members and undergrads who've been very helpful along the way with this, as well as the member of CDR who have been, one, helping us with that cheddar way, and two, just been very excellent resources for some of the tests and filtration I've been having to perform. And that's it.
We have time for one quick question. Brad?
Great talk, Becca. Does the type of incoming cheese whey make a difference for the functional properties?
So I would say the biggest thing I can think of right away is that, if you might have noticed, our WPC and our Whey WPPC, they're very orange. It's because we're using all cheddar. We're not blending them. Normally in industry, you'd have a blend of wheys. Also, you would probably like decolorize your whey, and to do that, use like peroxides, which is kind of seems like mildly nightmarish. But because of that, whenever I extract out my dairy lipids, I'm definitely noticing a pretty distinct orange tinge to that fat, which being that these are like visible spectroscopy measurements, I do think that they're kind of artificially inflating the scores a little bit, but because I used cheddar for all of the production, I think they're at least very comparable to each other. If I were to do this with like industry whey that was blended and decolorized, I would expect some of those to definitely decrease instead of just using this pure cheddar whey.
Thanks.
All right, sorry, we have to move along. Let's thank Rebecca one more time. Thank you.